So the smartwatch logic board I made a couple weeks back doesn't work. I could spend some time debugging it, or I could 3D print some motors. I 3D printed motors. So this is the first of the 3 motors I made. I made it a couple weekends back. It's a special type of motor called a laser galvanometer. They're pretty common in SLA 3D printers and in laser light shows. And so they're basically just a motor with a little mirror attached to the end. And if you point a laser at this mirror, you can point that laser in any direction you want, in one axis at least. To make it point in any direction, you need 2 of these motors, one for X and one for Y. If you think about it, these are just really fancy laser turrets. And you might be asking, what's the point of pointing a laser at a mirror, which then points in the direction you want? Why not just skip the mirror and point the laser where you want it to begin with? And so the main advantage of these motors are that they're really, really quick. Since you only need to move this tiny little mirror around versus moving around a whole laser, you can make this thing go really, really fast. It really makes a difference when you're working with high power lasers with something like 3D printing. On the other hand, since you can move the laser around a lot quicker, you can also create a persistence of vision effect, which allows you to draw images on the wall, something you can't do with the regular servo motor. And the way that these motors work is super cool, but I'll save that explanation for a future video. I haven't spent too much time working on the software for this motor. It does work, but it's a little janky. I've also partially harvested it. I might get around to improving it if I come up with an interesting project for it. So moving on to the other 2 motors I've been messing around with. These guys are called brushless DC, or BLDC motors for short. They're super common in commercial applications, everything from drones to electric vehicles to drills. This first motor is more of a standard kind. So we can see this part is a rotor which has little magnets embedded inside of it. And on the other hand we have the frame, which is called a stator. So these copper windings form what's called a solenoid. If we look at just one part of these, you can see it's basically just a piece of plastic with some copper wound around it. And if we run current through this coil, we'll actually generate a magnetic field. So if you run current through it in one direction, we'll generate a north pole here and a south pole here. And if we run current through it in the other direction, then we'll generate the south pole here and the north pole here. So let's say the south pole of the rotor is facing in this direction. If we turn on the current in this coil so that north pole faces towards the rotor, it will rotate towards it. And then if we turn this guy off and then turn this coil on, it'll rotate that way. And if we keep on repeating this process, you effectively start rotating the motor. And sped up, it looks something like this. So the actual algorithm I'm using to control this motor is a little bit more complicated. It's called space vector modulation and allows for the motor to run a whole lot smoother than if I were to just turn on one coil and the next. You can see it's basically allowed to go anywhere. It's not strictly locked to pointing towards one of these coils. I'll save the full explanation for a later video though. So I got this motor running up to about 5,000 RPM, but the downside is this motor doesn't produce a whole lot of torque. In fact, it basically produces no torque. I can stop the motor pretty easily by hand. I honestly don't even need to apply a whole lot of pressure. So normally these black pieces of plastic would be some kind of non-magnetic metal. So normally it wouldn't do anything, but if you run a current through the coil, it's actually able to magnetize the metal, so the metal forms a magnet which is much stronger than the magnet produced just by the copper alone. This is called an electromagnet. And Minute Physics and Veritasium did a really good video explaining how this works if you guys want to learn more. So the torque generated by the motor is more or less proportional to the force between the rotor and the stator. So the bigger the magnet I'm able to create here, the more torque I should get. And that's basically impossible with the 3D printed motor. There are some things you can do to improve torque, but even then you're probably not going to get a whole lot. So the second BLDC motor is called an Axial Flux motor, and in my opinion it's way cooler. So it's a pretty niche motor, but it's actually pretty common in EVs and smaller wind turbines. So instead of the 2 concentric rings we saw for the rotor and stator, it takes that and it puts the rotor and stator on discs. So this design is a lot easier to make at home, and there's actually a number of cordless designs for axial flux motors out there. They're also supposed to be more power dense than a typical BLDC motor, so they should be able to generate more torque within the same given volume. Basically the perfect candidate for 3D printing. A lot of people have actually done it already. Honestly, it looks a whole lot cooler in my opinion too. So this initial prototype I made is a little janky at lower speeds, and it's starting to fall apart, but even given how janky it is, it's still able to go really fast. I got this guy going up to around about 30,000 RPM, which is kind of just crazy. So both of these motors are driven by this mildly janky controller board I made a few weeks back. Despite being called a DC motor, they're basically AC motors in disguise, and they require special controls to make them spin properly. Right now they're just going in open loop, so I'm more or less just feeding them a 3-phase AC signal and hoping for the best, but I'll eventually get around to writing a proper controller for it. I'll probably make a video explaining how all that works at some point too. I'm also going to upgrade this board at some point. It's like I said, it's a little janky and there's a whole bunch of jumper wires going everywhere, so I'm probably just going to take it all and cram it into one board. I could use something like the O-Drive or the VESC, but it's a lot more fun to make my own. So just a quick update on the Axial Flux motor. I worked on it a little bit, redid some of the windings so there's no longer windings hanging out of every corner. I might have actually made it a little too good now. It runs super quietly, so even though it's going pretty fast, you can hardly hear it make a sound, which is... That's about it for this video. I'll probably get around to finishing the smartwatch soon, so keep an eye out for that. I'll be posting more updates on these motors at some point too, once I make some more progress.